My name is Nadav Har'El. I work for Cloudius Systems, and I want to present OSV, which is indeed an operating system for virtual machines. Let me to hold it. Yeah. Okay. So as you probably all know, virtual machines are very useful and are everywhere. There are a lot of alternatives to virtual machines. We have containers, we have Pekka processes, we have a lot of other ideas of doing things besides virtual machines. But virtual machines are nevertheless still very common and useful on the cloud, on a lot of cloud providers. And the virtual machine needs to run, obviously, a guest operating system. And what people have been doing is simply to take an existing general purpose operating system that they've been using for many years on physical computers, such as, for example, Linux, and run this on the virtual machine. And the question is, given that these operating systems have been designed many years ago for the needs of physical computers and a lot of other needs, and not specifically for virtual machines, can we do something better if we design an OS specifically to be run on virtual machines? So the system we developed, we call it OSV. It's a new operating system designed specifically for cloud virtual machines. And I tried to list the goals of how we designed OSV, to list the goals in its design. So first of all, the intention is to run existing cloud applications without too much modifications. So we can take, we want to be able to take Linux executables without needing to rewrite them completely or anything close to that. We want to take existing executables and just be able to run them on OSV. We want these to run faster in OSV than on Linux, so it will have some advantage. Otherwise, it's not clear what's the point in writing a new operating system. Besides running existing executables, we also want to explore what kind of new APIs could this operating system have, so it would give the applications even better performance. And because people find it hard to adopt new APIs, one of the ideas is to try to take some common runtime environments, such as a JVM, and modify that to use new APIs. And once we do that, basically all the unmodified applications that run on top of the JVM can also run with the additional improvements without being modified. Another goal of OSV is to be much smaller than Linux. We want to have a small image and very quick boot, much faster than 1 second. And there are several interesting advantages in this. And for example, in the management of virtual machines, there's a lot of work on how to reconfigure Linux guests, how to take a running Linux guest and change its configuration to do something a bit different. And if the boot is so quick that it's just as fast to start a new guest instead of reconfiguring an existing one, it simplifies a lot of things. And we want OSV not to be not to be limited to a specific hypervisor or platform. We want it to be generally useful. So it's already working on 64-bit x86, and the 64-bit ARM port is in progress. It's already running some Hello World programs, and hopefully it will soon be fully working. And OSV already works on KVM, on Xen, on VMware, VirtualBox, and also on Amazon EC2 and Google compute engines. Okay, so, and also another goal of OSV is to become a platform for continued research on virtual machine operating systems. So OSV is open source. You can see here the link. You can go and get it and change it. And the OSV community really encourages innovation. It's new source code. It doesn't have a lot of legacy. We really want to try new things. So if anybody has an idea of something you think belongs in an operating system for virtual machines, this is a good place to try it. It's a small code base compared to Linux. It's written in a modern programming language, C++11, which is, many people are not yet familiar with it, but actually C++11 has a lot of interesting benefits. It has built-in support for SMP programming, for atomics, memory ordering, some interesting things for writing an operating system. It has a very rich and very high-quality standard library, so it's very nice to program a kernel actually in C++11. And you can try a lot of things on OSV because it's not limited to a particular hypervisor or application programming language or type of application. And of course, it supports SMP guess. It's not just a uniprocessor guess. Okay, so now I want to survey just a bit of OSV's design and implementation. I can't, of course, cover in this time a lot of detail, but there's more detail in the paper and, of course, in the source code if somebody wants to see the whole thing. So, okay, so first of all, how can a virtual machine operating system be different than a general purpose operating system? So I think the most obvious or the biggest difference is that one of the most significant capabilities of a general purpose operating system is process isolation, to isolate different processes from one another, and also from the kernel. And actually in the cloud, this is not as important as it used to be on general operating systems, because if you look now at the cloud stack, now you have both the hypervisor and the guest operating system doing isolation, because the hypervisor already can run several different VMs and isolate them from one another. So if some application needs to run two different things which are isolated from each other, it can run as different VMs instead of different processes in the same VM. So basically, one of the key ideas in OSV is that it is enough to run a single application on the VM. And I want to know that it's already common. People are already doing this, already running single application on each VM as part of the scale-out trend, where you, for example, some big web application is composed from, I don't know, a dozen Memcached VMs and then a dozen web servers, and you get a lot of small VMs doing one thing. And of course, once we only support a single application, the OS code is simpler and cheaper. There are a lot of costs in this isolation which can be eliminated. So OSV runs a single application, which means a single process, but of course multiple threads within this process, which all share the same address space. And also the kernel and the user space also share the same address space, and there's no protection between them because basically there's just one application running on the kernel. So if the application crashes the kernel, there's no harm to any other application. So once we have no protection between user space and kernel, system calls become just ordinary function calls. So OSV is basically a library OS. So OSV runs the Linux shared objects by implementing an ELF dynamic linker. You just take a Linux shared object and it runs it, and it resolves calls to the glibc ABI. It resolves into functions inside the OSV kernel. Even calls which are thought to be system calls on Linux, for example, read, are just ordinary function calls implemented in the kernel and have none of the traditional overheads of system calls, such as copying parameters between user space and kernel space and all these other overheads of system calls. Okay, so OSV, because we want to run existing executables, we did a lot of effort to get Linux compatibility to implement most of the Linux glibc API. Some things we can't support and we don't support, like fork and exec, because this doesn't fit a single application model. Another design point in OSV is that we wanted to completely avoid spin locks. Spin locks are, I mean, most kernels use them. It's a very common technique to write kernels on SMPs, but there's a problem with spin locks in virtual machine operating system because they cause the lock holder preemption problem. And this can be worked around, for example, by using para-virtual locks, but in OSV, because we designed it directly for virtual machines, we decided we want to completely avoid spin locks. We simply do not use spin locks at all in the kernel. And we used a few tricks to do this. It's explained in much longer in the paper. So most of the kernel work is done in threads, which can use sleeping mutex and don't need spin locks. The mutex is done with a lock-free algorithm. And also the scheduler, which obviously cannot sleep, also uses lock-free algorithms. And another interesting piece of OSV's design is that we, instead of using the traditional network stack design, we took a design from Van Jacobson from 2006 called network channels. And the idea is that we want to reduce the locks, the lock contention, and cache line bounces in the network stack. Because the typical network stack, you have two threads. Basically, you have the interrupt thread, which gets packets and then execute the TCP protocol and writes to a buffer of characters. And then you have the application thread, which reads from these characters. So these two threads fight for locks, for the cache lines, and so on. And the idea of the redesigned stack is that the interrupt thread only collects packets and doesn't even touch the content of these packets. It just collects them into lock-free channels. And the TCP protocol is actually executed when the application does the read. So this design improves the performance on modern SMP machines. And okay, I'll have to go a bit quicker. So OSV, the core of OSV is completely new code, all the dynamic linker, memory management, scheduler, and all sorts of virtual hardware drivers that we only have a few of those because we don't need to support all the legacy hardware or thousands of different hardware because we only run on virtual machines. And when it was appropriate, when there was good open source code that we could reuse and it wasn't part of the main OSV difference, we reused existing code such as a ZFS file system from FreeBSD. Network stack, we started with FreeBSD's network stack and then we modified it to use Van Jacobson's network channels. And beyond the Linux API, I mean, we want to run existing Linux programs, but we also wanted to further improve the performance by offering new APIs because the existing APIs still have, for example, a read system call needs to copy the data into a user space buffer, but since we only have a single application, we could have just have the data being read directly into the user's buffer with zero copy APIs. So here are some ideas. I don't have time to cover them. It's explained in more detail in the paper. We tried some zero copy APIs. We wrote about the idea. We didn't actually try this to give the application, the single application, direct access to page tables to improve, for example, garbage collection performance. We added a shrinker API, which gives the single application a better access to all the available memory, so it doesn't need, for example, the JVM doesn't need to choose a heap size in advance. It can fill all the available memory. And like I said before, the biggest obstacle to new APIs is to get them adopted, and what we think is a good idea is to use them in some runtime environments such as JVM, and then all unmodified applications can also make use of these APIs. Okay, so the evaluation. For evaluation, we compared OSV guest to a Linux guest. We took a Fedora 20 and disabled the firewall, and ran this on a KVM host, and you can see all the details in the paper. For example, we ran Memcached with UDP, single vCPU. We ran the MEMASLAP benchmark, and the OSV performance was 22% better than Linux. When we this was an unmodified Memcached, the normal Memcached that runs on Linux, that can also run on OSV. When we re-implemented Memcached to use a new zero-copy packet filtering API, the performance was much better than the regular Memcached, 290% better. For spec JVM, which is a Java benchmark makes little use of OS services, we didn't get much improvement as expected, only 0.5%, but it's a good correctness test. The fact that it ran and all the tests got the right results, it was a good test that OSV actually does the right thing. And we also ran some micro benchmarks. NetPerf is the stream is 24% better. The latency is 37% lower. Context switches are much faster on OSV than they are on Linux, 3 to 10 times better. We showed how the JVM Balloon idea improves things. And some unofficial results after we wrote the paper, we also got significant improvements on Cassandra and Tomcat. And basically, I'm out of time, so thank you. You're welcome to come see our site, get the source code, join the mailing list, and join the project. Thank you.
Hi, I'm Yahui from Binghamton University. I have one question about the OSV. As you said, there's no protection from the user space to kernel space. So what if some user space program wants to do something evil? How to protect this?
Yes, so basically if it does something evil and, I don't know, writes to the kernel memory or whatever, the only thing it can damage is itself, because this program is the only thing running in this VM. And it cannot go outside the VM because this is what the hypervisor guarantees. The hypervisor makes sure the VM cannot escape the VM. But inside the VM, we only have a single process running, and it's kernel. This is basically the idea of a library OS, that you have just you have the kernel servicing only one application. You don't, so it cannot do any damage.
Okay, thank you. So I have one.
Dan Williams, IBM. So I also have a question about the protection. Have you found it a lot more difficult to debug your applications? Because you have, if you have some bug in the kernel, it could start doing some memory corruption or something into your application, and it would be kind of hard to narrow that down. Have you seen
Yes, so at this point we are more working on the kernel itself than the application, so we expect kernel bugs. But you're right that if there are kernel bugs, it can crash your application, and you're never sure if it's a kernel bug or application bug. But it's not very different than, also if you program on Linux and you come across a kernel bug, it can ruin your application, and it's hard to debug. And the idea is not to have kernel bugs. You try to avoid that.
We have one really fast question.
Okay, Andy Tannenbaum, Flu University. About 20 years ago, one of my students from at MIT did a kernel, which is a Visual Library operating system. Strikes me as this is part two.
Yeah, so of course in the paper we mentioned exokernels as prior work, and in the exokernel you have this exokernel outside and the library OS with each application, and here you have, instead of the exokernel, you have the hypervisor. You have this takes on the role of the exokernel, right? Yeah, it's a new application of the same idea. Yeah.